Hey everybody, sorry I couldn't be in class today, but I will be with you hopefully next time we come to class. Here's the lesson for today. You should already have your notes from the sub. They should already be glued into your notebooks. Let's go ahead and get started real quick with the review from what we talked about before we went to Thanksgiving break. Again, really quick, review the structure of an atom. Atoms are made up of protons, which are positive, have a mass of 1. Neutrons are neutral, also have a mass of 1. And electrons are negative, have a mass of 0. The protons and the neutrons are found in the nucleus. The electron is found outside the nucleus in the electron cloud. When we're identifying atoms, we use what we call the atomic number or the number of protons. Every atom of each element has the same number of protons, and that's what we call the atomic number. So in these examples here on the screen, every atom of boron, because it has an atomic number of 5, has 5 protons. Carbon, every atom of carbon has 6 protons. The important thing here is the number of protons determines the identity of the element. When we're weighing atoms, it's very, very, very important that we don't use the number on the periodic table. Do not use that. When we weigh atoms, this is what we call the mass number. It's the number of protons and the number of neutrons. It's always a whole number. Okay, it is not the same as the atomic mass that you see on the periodic table. We are not going to use that number yet. We will use it later, but we're not going to use it now. So for the mass of our atoms, you take the number of protons, add it to the number of neutrons, and that's how you get the mass of your atom. Do not use the atomic mass on the periodic table. Let's review what isotopes are. Remember, isotopes are atoms of the same element that have a different number of neutrons. For example, here in this example, we have 3 isotopes of hydrogen. They all have 1 proton, that's the pink circle. They all have 1 proton, that's what makes it hydrogen. What makes them different from each other is the number of neutrons, the orange circle. The one in the middle doesn't have any neutrons, the one on the left has 1, and the one on the right has 2. Different isotopes have different mass numbers because the number of neutrons is different. Their masses are different because the number of neutrons is different. The number of protons is the same. Some isotopes are not stable. We'll talk about that, what that means in a second. So let's review our notation. So I can do it this way, where I just have the atomic symbol and then the mass number after it. Or I can write out the entire name and then put the mass number after it. This is what we call hyphen notation. I don't have to tell you the number of protons because you can look it up on the periodic table. You can look on the periodic table and you can find the U, you can find uranium, and you can see that, oh, this has 92 protons, which means the rest of my 235 has to come from the neutrons. Something new, what we call the nuclear symbol. You might have seen this before. It's very similar to our hyphen notation. We just change where we put the numbers. So you'll see that right here, here's my element symbol, still a U, still uranium. Now I am going to give you the atomic number. Sometimes. Sometimes it'll be there, sometimes it won't. We don't actually need it. If we know what the element symbol is, we don't need that number. But sometimes they put it in just to be nice. And then of course this 235 up here is my mass number, which again is protons plus neutrons. So this is what we call the nuclear symbol. So let's go ahead and practice. As we go through these, I want you to pause the video, try to work through it on your own, and then resume the video again once you have an answer so you can check. All right, so let's start with aluminum. Aluminum, I will tell you, has 13 protons. If you didn't know that, you could also look it up on the periodic table. It is element number 13. This particular atom of aluminum has 14 neutrons. So go ahead and pause the video. Try to fill in the remaining 3 numbers. Once you have it, restart the video and check to see if you're right. Okay, so the first thing that we have to remember is that protons is the atomic number. So number of protons, same as the atomic number. Again, we can get that straight from the periodic table. We also know that the number of electrons is the same as the number of protons. So those 3 numbers have to be the same. There will come a day when they're not the same, but right now they have to be the same. So how do we find our mass number? Remember that our mass number is the number of protons plus the number of neutrons. Add those together, we get 27. So let's go ahead and practice with our hyphen notation. So here we have uranium-235. Go ahead and pause the video, fill in your 5 numbers. When you have an answer, restart the video again and check to see if you're right. So let's go ahead and get started with our mass number. That one's easy because it's right there in the name, uranium-235. That's our mass number. The next one we're going to do is our atomic number. Again, you look this up on the periodic table, you find uranium. It is number 92. That tells us our atomic number. What that atomic number also tells us is the number of protons and the number of electrons. Remember, those have to be the same. Now, how do we find the number of neutrons? Well, we know that our total mass is 235. 92 of that comes from the protons, so we just subtract those to find the difference, and that's going to tell us that there are 143 neutrons. One more practice with our new nuclear symbol notation. So here we have Ag, which is the symbol for silver. We have 108 and 47. Go ahead and try and fill out your 5 numbers. Once you have them, pause the video first. Once you have them, restart the video and double check to make sure you have the correct answers. So let's go ahead and get started with our number of protons. That's the number on the bottom. That's our, we can also look that up on the periodic table. If the symbol doesn't have a number on the bottom, we can look that up, and that gives us 47. That is also our atomic number. It's also our number of electrons. Remember, those 3 numbers have to be the same. So our mass number is going to be 108. That's the other number. It's always going to be the number on top. How do we find the number of neutrons? Well, if our total mass is 108, the number of protons is 47. We subtract those, and that gives us a number of 61 neutrons. If you had any issues with any of those examples, please, please, please come talk to me. I know it's been a while, but please come talk to me because this is going to be very, very, very important for your test, which is going to be next week. So if any of that review was confusing for you, again, please come talk to me. All right, let's get into the new lesson for today, carbon dating. So real quick, here's a crash course, very briefly, on radioactive decay. We'll talk more about radioactive decay in the spring, right after spring break. So remember, I said that not all isotopes are stable. What that means is that sometimes those nuclei will fall apart. This is what we call radioactive. When the isotopes are not stable, they fall apart. Over time, the number of protons and the number of neutrons may change. This change is totally random. What I mean is, which atoms change is going to be random, right? We don't know if it's going to be this one or that one, or which atom it changes is totally random. The original atom, so some vocab, the original atom is what we call the parent atom. The new atom that we create after our radioactive decay, is what we call our daughter atom. So here's an image for you. We have our parent isotope here. We go through some sort of radioactive decay, and we have a daughter isotope, a daughter atom. So we have our parent that is not stable. It goes through a radioactive process, and we create a new atom, what we call our daughter atom. So let's talk briefly about what we call half-life. No, not that half-life. So a half-life is the amount of time it takes for half of the parent atoms to turn into the daughter atoms. Remember, it is completely random which atoms are going to decay, which atoms are going to change. But on average, after a certain amount of time, half of those atoms will have changed. It is different for each atom, for each isotope. They have different half-lives. Some are more than 4 billion years for a half-life. It takes a very, 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 very long time for some of those parent atoms to turn into their daughter atoms. Some half-lives are very short, less than a second. It does not take them long to change. We can use half-lives to determine the age of rocks and fossils and things like that. Because what can happen is, if I have a certain amount of my isotope, if it has a 5-year half-life, meaning it takes 5 years for 50% of that to go away, I can use this as a clock to see exactly how much time has passed from when I started to when I ended. So for example, if I have 25% left over, that will tell me that my isotope or my sample is about 10 years old. If I have 3.125% of my isotope left, that means that it is about 25 years old. So we can use isotopes, this half-life of isotopes, to help determine how old something is. So let's talk briefly about our carbon isotopes. Carbon isotopes are very helpful when we're trying to identify, or we're trying to find out how old something is that was once alive, because all living things have carbon. So real quick, carbon 12, again, 6 protons, 6 neutrons. This one is very stable. Carbon 13 is also stable. This one has 6 protons and 7 neutrons. That's what that 13 tells us. Carbon 14, this is our radioactive isotope of carbon. This one has 6 protons and 8 neutrons, but because it's radioactive, that is going to change. Because carbon 14 is radioactive, the number of protons and the number of neutrons is going to change. This is what we call carbon dating. Carbon 14 decays to nitrogen 14. One of those neutrons changes into a proton, and our atom changes from one element, the element carbon, into a different element, the element nitrogen. The half-life of carbon 14 is 5,730 years, which means after 5,730 years, half of the carbon 14 will have decayed to nitrogen 14. Now, when things are alive and we're putting carbon, for example, humans, or basically any animal, any plant, anything that's alive, we're constantly replacing the carbon in our bodies. Some of that carbon is going to be carbon 14. About 0.0001% of all of the carbon in your body is carbon 14. And as it decays, you replace it with new carbon through your food, as you're breathing, whatever. You're replacing that carbon, and all living things do this. We have a constant ratio of carbon 14 and carbon 12 in our bodies. But what happens when we die? Well, when we die, that carbon isn't getting replaced anymore. And so it's decaying to nitrogen and it's not getting replaced. And so our ratio of carbon 14 to carbon 12 changes. And so we can use the percentage of carbon 14 left in a body, whether it's a plant or an animal, and we can get a pretty good idea of how long ago it died and how long ago it was alive. This is what we call carbon dating. Again, we look at the difference in the amount of carbon 14 in a body. So let's go and look at our corpse. Remember, we found a body in Greenland where we think Commander Hall was buried, but we don't know if this was actually Commander Hall. If we can figure out how long ago the body was buried, then we can determine, is this the correct gravesite? Could this be Commander Hall? All right, go ahead and make sure you've got your notes, you've got something to write with as we go through these questions here. So a sample of bone from the corpse shows the following percent of each carbon isotope. Again, this information is in your notes. It's right in the middle. So carbon 12, carbon 13, and carbon 14. Look at those numbers. I'm not going to give you the answer right now, but look at those numbers. Feel free to talk to the person sitting next to you, work together in a group, looking at these numbers. What do they tell you? Remember what you know about radioactive decay. Remember what you know about which isotope of carbon is radioactive, which isotope of carbon is going to change, what happens when living things die. So take a look at this. Go ahead and pause it, have that discussion. Okay, from these results, we can see that only about 1% of the carbon 14 has been converted to nitrogen 14. If we go back, only about 1% of this has changed. What that means is that 99% of the carbon 14 is still in the bone. Only 1% has decayed. So using the graph on your page, determine, get an idea, estimate how old do you think the bone is? How long ago did this person die? Again, we're about 99% of our carbon is still there. Here's 95%. This would be 97.5. So about 99, we're going to be right about here. So about, if we're to estimate, about how long ago did this person die? So that's our first question down at the bottom. Go ahead and answer that. And when you're done, based on the estimated age of the sample, do you think this could be Commander Hall? This could have been his body. Okay, once you have the answers to those two questions, then we're done for today. Again, make sure that your notes are glued into your notebook. I will be back tomorrow or Wednesday, and we will continue on with our lesson. With our chapter. We are just about done with this section. We will take a test next week. I will also have a study guide for you for those of you who are going to be taking the final, so you know what you need to be preparing for. If you have any questions, feel free to shoot me an email, send me a text. Otherwise, I hope you guys have a great day, and I'll talk to you later. Bye.